Okay, so today we are going to look at exponential growth a little bit closer. What we did last lesson was we looked at a sort of exponential growth with this compound interest formula. And just as a quick little review, if you remember, this compound interest formula really is not exponential. It's a step function where we start off with the money that we put into our account, and then it stays that way until we compound it. And if, let's say, we just our compounding rate was, our rate was, let's say, just 100%, then this would double, and then it would double again, and then it would double again, and then it would double again, and I've run out of paper. So the actual steps have an exponential growth to them. So like from here to here, if this is 1, this would be 2, this would be 4, this would be 8, and the steps have an exponential growth to them. But the function itself is not exponential, it's a step function. Because this function cannot be written in the form a times b to the x. It doesn't work. This number in here is not a constant, because the n causes this number in here to change every so often. You're like, yeah, well, the n is a constant and the r is a constant in this problem, and we're just doing it in terms of t. That's true, but the money doesn't increase constantly. It only increases over intervals. So from, let's say that this was yearly. So after the first year, right before that year turns over, I still have the same amount. It's a constant function. Then it jumps exponentially to another constant function. Then it jumps exponentially to another constant function. So while this is the beginning of exponential, it doesn't actually count as an exponential function. It's a step function where the steps exhibit exponential growth. And what you had to complete, part of what you had to complete, was this last couple of pages where we were trying to figure out the amount of money in an account with certain specifics. And we noted it started off with a dollar, then as we shrink the compounding interval, $2, 2.25, 237, 244, 252, 261. It seems to be increasing, but it's not increasing without bound. Here it doesn't increase at all because our 1 year doesn't incorporate the compounding interval. But then it doubles. It increases by $1. Then it only increases by a quarter. Then it only increases by 12 cents. Then it only increases by 7 cents. Then by 8 cents. Why did that go up? Because of the rounding. So this really is slightly smaller than that. Then after that, by 9 cents. Again, it dealt with the rounding. Then by, here we go, 5 cents. Then by 2 cents. Then by 1 cent. Then by 1 cent. And, well, if we try to use a calculator and we graphed our function 1 plus 1 over x to the x, and you went to the table and you looked at all the values when x was really big, you probably got something like 2.71828 and so on. And if you wrote it as a decimal, that's fine, but this number should be a little familiar to you. The calculator rounds it off, but really this, when we look at the end behavior of this function, is e. And so then the question becomes, well, what happens if we let the compounding period, this n, the number of times we compound per year, go off to infinity of the general p1 plus r over n to the nt function? What happens to this compounding function? Well, the steps wind up getting smaller and smaller and smaller in length, and the gaps between the steps wind up getting smaller and smaller, till eventually you wind up with a nice smooth function. And in fact, as n gets really large, and you're going to prove this next year in calculus because we don't have the tools right now, this formula actually becomes the formula for continuous compounded interest. This means that at any given instant, money is being put in the bank. Not every second, not every tenth of a second, not every millionth of a second, every single instant. It's so many instances that we can't even measure them. The number of instances over any given interval is aleph 1. All the numbers from 0 to 1 second, all of those numbers in between 0 to 1 second, money is being added into this account. You name a number, 1 over 10 million. Interest is being calculated and put into an account that has continuous compounded growth. That's the formula we're going to use. And I'm not going to do any examples here. The textbook has some examples which we'll look at. But this is really the first instance of exponential growth. And this is a special case. This E comes from the fact that this end behavior is actually equal to this number. And in fact, a lot of mathematicians actually define the number E to be equal to the end behavior. So it's not coincidental. They said, this end behavior is a number. 2.71828, blah, 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 forever. It comes up so often we need to give it a name. Let's call it E. In the same way, when you're dealing with a circle, oh, okay, so I need to know how many times does this diameter fit into this circumference. Okay, that is a very important number. Let's call it pi, whatever that number is. Same thing, E is just whatever this number is. And that's how it's defined. So this is one example of an exponential function. And this exponential function is different than all the other ones we're going to be looking at, because in this case, the E comes from this end behavior. And that's very important for you to distinguish. Here, the E comes from the end behavior. So remember that. Because today, we are going to be looking at, I think this is the right handout. Yep, okay. We're going to be looking at exponential functions in general. So just a little reminder that our formula for or the definition of an exponential function is a function that can be written as ab to the x, where a is not equal to 0, b is greater than 0, and b is not 1. And if you're wondering about that, well, if b is 1, 1 to any number is 1, and then we would just have a times 1. So this wouldn't be exponential, it would be constant. If b is 0, we wind up with all sorts of problems. If x is positive, that's just 0, the whole thing is 0. If x is 0, well, 0 to the 0 is undefined. And if x is negative, we wind up getting 1 divided by 0. So that would be a problem if b is negative or if b is equal to 0. And then we say a can't be 0, because if a is 0, 0 times any number is 0. This would just be the constant function 0. So those are the reasons why we define our function as we do with the a and b values. Okay, so the half-life of a specific radioactive substance is 1.5 years. If they're initially 250 grams of the substance, find an equation that models this radioactive decay. Well, radioactive decay is exponential decay. The amount that decays is directly proportional to the amount that's there. So the bigger the amount of substance, the quicker it's going to decay. And the less amount of substance, the slower it's going to decay. And that makes sense. If I had something that decayed by half every year, if I started with 100 grams of it, after a year, 50 grams are gone. That's a huge number. But if I start with 2 grams, only 1 gram winds up being gone. And that's much smaller than 50. So this is going to be exponential growth, radioactive decay, or exponential decay in this case. So I need a function a times b to the x. So how do I get that? Well, I do what we did for linear functions and quadratic functions. I try and find points that are going to be on this graph. So I know there are initially 250 grams. That means initially, when my time is 0, x is 0, I'm going to have 250 grams of this stuff. So that's one point that's going to be on the graph. I also know that the half-life is 1.5 years. A half-life tells me how long it takes for half of my substance to decay. So after 1.5 years, half of my substance will be gone, which means I'll only have 125 grams left. And now I have 2 points. And if you notice, when I'm trying to solve for a function, I need to solve for a and b. That's 2 unknowns. I have 2 points, 2 values. I have 2 unknowns. I can get 2 equations, and I can solve this. So let's see. When x is 0, y is 250 equals ab to the 0. And when y is 125, x is 1.5. And now I can solve this. And this is kind of easy because b to the 0 is 1. And I know it's defined because in my definition of exponential functions, b has to be positive. So since this is 1, I get that 250 is equal to a. Nice. So now I can solve for b. I plug the a in here. 125 equals 250, b to the 1.5. Divide both sides by 250. And you'll note I get a 1/2. And that's not a coincidence. I'm dealing with something called half-life. So my exponential portion should have something to do with that rate of 1/2. The question now is, well, how the heck do I figure out what this is? I could take the 1.5 root, but we really don't talk about decimal roots. So instead, I'm going to rewrite this. 1.5 is 3/2, and I'm going to remind you to solve a variable raised to a numeric power, I just raise both sides to the reciprocal of that. So I get that b is equal to 1/2 to the 2/3, or if I put it in my handy dandy calculator, because these are application problems, it would be okay for me to round. I have, let's see. Oops. 1/2. And please, please, please make sure that you use parentheses. Otherwise, if you don't, you might wind up raising just the 1 to the 2/3. This whole thing to the 2/3. And we get that b is about 0.63. So then my function, f of x, will be a is 250, b is 0.63 to the x. Now, I could have gone with 0.6299. I went with 0.63 just because of the rounding, but let's make a convention that we'll go to 4 decimal places. We'll round to the nearest 4 decimal place, which for this problem, I knew ahead of time, the 6 rounds up, this would be 0.6300. So again, our convention will be, we're going to round our numbers to 4 decimal places, unless it says otherwise. So how much substance will remain after 4 years? Well, now we're just looking for f of 4. So f of 4 is equal to 250 times 0.63 to the 4th. And again, this is going to be an approximation because we rounded, but that's okay. These problems are applied, so we're dealing with chemists, not mathematicians, and a lot of times the numbers they get are good enough. So now this is just a calculator question. 250 times 0.63 to the 4th is about 39.3824, 4 decimal places, grams of the substance. And just a little note, if I had left b as 1/2 to the 2/3, just to give you an idea, instead of rounding it, this would be 1/2 to the 2/3 to the 4th, and that is an accurate way of writing it. Notice we get 39.37. So already 0.3725. So already our answer is slightly off. But again, for our purposes, these are applied problems. We'll be okay with the slight error there. If we wanted to, we could actually calculate what the error is, but we're not going to get into that. All right, same game. Suppose 600 grams of radioactive substance are present initially. So that means one point is going to be 0, 600. And 3 years later, only 300 grams remain. So here, I'm not specifically told what the half-life is. I can figure it out. After 3 years, I've lost half my substance. The half-life is 3. And it's a half-life, so the 1/2 is probably going to come into play somewhere. But this could have easily said 3 years later, only 200 grams remain. And then this would be 3, 200. So again, find an equation for this. Okay. So let's see. 600 equals AB to the 0. And 300 equals AB to the 3. So already we get that A is 600. I can plug that in for my A over here. I get 1/2, plug it in for A, sorry. I get 1/2 is equal to B cubed. So in this case, I would raise both sides to the 1/3. And B is equal to 1/2 to the 1/3, which is approximately, and the nice thing about this calculator is I just did 1/2 to the 2/3, so I can just go back. Whoops. I hope I can go back. Where was it? Well, I lost it. Oh, well. So I'll have to just do alpha y equals 1/2 to the 1/3. And we get that B is about 0.7937. 0.7937. So then our function will be A, which is 600, B, which is 0.7937 to the x. Now determine approximately how much of the substance will remain after 4 years. Okay, once again, that's f of 4. That will be 600 times 0.7937 to the 4th, which is 0.7937 to the 4th. Whoops. 0.7937 to the 4th. Times 600, 238.1095, 238.1095 grams. And again, just to give you a bit of an idea here, if instead I raised this number to the fourth and then multiplied it by 600, as you can see, if I went with the exact answer, it'd be 238.1102. 238.1102. But we chose to round. Now, what's the difference? Well, if we want to be more accurate, we should use the 1/2 to the 1/3. But I know that that's kind of a pain, so I'm willing to allow you to round to begin with and then solve the problem. Unless as a class we want to come up with a convention, I'll leave that up to you. If you want to come up with a convention so we're consistent that you can't round until the end, we can say that. We can say don't round until the end. If you're okay with rounding mid-problem, it's really not a good idea to do it. Next year on your AP exams, if you do it, you'll be penalized. So you tell me what you want to do, and we can come up with a convention for the class. So I guess you can send me private comments or comment on this below, and just let me know. Okay. Next problem is a little different because we're not given an initial value. A radioactive substance is decaying such that after 2 years, there are 300 grams remaining. Okay. And after 5 years, there are 100 grams remaining. Okay, no problem. Find an equation that models the radioactive decay. Okay, so I know this is going to be y equals ab to the x. And I know I've got, let's see, 300 equals ab squared. And I have 100 equals ab to the 5th. And, ooh, I don't have a nice little trick anymore where I can just solve for a right away because these just don't, the b's don't cancel out because I'm not raising anything to the 0. You could say, okay, let's raise both sides of this to the 1/2. I could do that, but then ab squared square root, and then I'm dealing with extra roots. I could raise both these sides to the 1/5, and then I'm dealing with extra roots again. There is a way of doing this, solving simultaneous equations or a system of equations that are exponential. With linear equations, if you remember, we added and subtracted them because the rate of change, the slope, was dependent upon the difference in our x and y values. If the difference in x is the same, the difference in y had to be the same. With exponential functions, if you remember, it was the ratio that had to be the same. So instead of adding and subtracting, I can put my equal sign in there, divide. And note what dividing the equations does. 300 divided by 100 is 3. A divided by a cancels. And I know that I can do this because a is never going to be 0. And b squared divided by b to the 5th is b to the negative 3. Which means, to solve for b, I raise both sides to the negative 1/3, and I get that b is equal to 3 to the negative 1/3. For this problem, I'm going to leave it exact for now. So then how do I figure out a? Well, perfect. I just take my b and I plug it in and I solve for a. So you pick one of the originals. I'll pick the first one up here. So I have 300 equals a times b squared. So then I divide both sides by that. I get 300 divided by 3 to the negative 2/3 is a. All right, let's see what that is. So 300 divided by 3 to the negative 2/3 is about 624.0251. And b is 3 to the negative 3rd, 3 to the negative 1/3. That would be 0.6934. So my function for this, and I kind of ran out of room here, but that's okay. My function f of x will be a 624.0251 times b 0.6934 to the x. And now determine approximately how much of the substance was remaining after 4 years. Well, again, that's just me finding f of 4. So in this case, if I find f of 4, it is what it is. I'm not going to go through that. So we used this definition of exponential function, a times b to the x. In part A of questions 1, 2, and 3, you model the situation using an exponential function of this form. Oh, we used x instead of t. We could have used t for time. What did the A represent in these problems? Well, the A was the initial value or initial amount of whatever the substance was. And what was B? Well, if we go back and we look, B is the growth rate or the decay rate. The half-life here was 1.5 years. That means after 1 year, I'm only going to have 63% of my substance left. After 2 years, I'll have 63% of 63%. After 3 years, I'll have 63% of 60. So the B represented the decay rate. Here, this is 79.37%. Here, this is 69.34%. So this was the rate of growth or decay as a percentage of the initial amount. So if, well, the rate of growth decay, I guess, per year. So after 1 year here, I would lose about 69% of my substance. Or rather, I'd only have about 69% of my substance. I would lose about 31% of my substance. After 2 years, I would have 69% of that. After 3 years, I'd have 69% of that. After 4 years, I'd have 69% of that. So if the decay rate were 40%, the B would be 0.6. If I'm losing 40% of my substance every year, that means after the first year, I have 60% of it left. So this is one way to model using the exponential form a times b to the x. But as you'll learn in calculus next year, the number e is so important, and it actually, mathematically, is tied directly to this idea of exponential growth and decay. When we do calculus next year and we do some differential equations, you're going to see this e pop up when we talk about when something is directly proportional, when a rate of change is directly proportional to how much is there. So another form that we use to write exponential functions is a e to the kt. And I said this earlier, and I'm going to say it again. This is a completely different form than PERT, P-E to the RT. They are different. This represents exponential growth and decay in almost all situations. This represents continuously compounded interest. The P here represents the principal amount. The A here represents the initial amount. Oh, they're the same. The R here represents the interest rate. The K here does not represent a growth rate or a decay rate. The K is not a rate in this problem, and we're going to see that in a little bit. The K is not the rate. This K is not the same as this B, and we'll see that. So, same problem. The half-life of a specific radioactive function is 1.5 years. They're initially 250 grams. So initially 0, 250, and after 1.5 years, I've lost half of it. That's 1.5, 125. It's the same game, only I use this form instead. So when y is 250, t is 0. And when y is 125, t is 1.5. And you'll notice these equations have two unknowns, an a and a k. We know the value of e. It's a constant. Like pi is 3.1415 whatever. E is 2.71828 whatever. We know this. We only have to find capital A and lowercase k. So luckily, like before, k times 0 is 1, e to the 0 is 1. I figure out my A is 250, the initial. That comes from the fact that when I plug in 0, I'm just wind up with it. So I can solve this the same way as I did before. This is 1.5k. Divide both sides by 250, and we get 1/2 equals e to the 1.5k. To solve for a variable that is in an exponent, we must take a logarithm of both sides. And if I want to eliminate the base, what we do is we take the logarithm whose base is the same as the base we're trying to eliminate. So in this case, base e, or natural log. And the reason we do that is now this 1.5, with our log laws that we practiced, can come to the front. And we get ln 1/2 equals 1.5k times ln e. And if you remember, ln is just log base e. Well, log base anything of itself is 1. This is asking e to what power gives me e. This is 1. And 1 times anything is that thing. So we're left with ln of 1/2 equals 1.5k. So k will be ln of 1/2 over 1.5, or approximately ln of 0.5 divided by 1.5, negative 0.4621. So the function f of t is going to be a, 250, e to the negative 0.4621t. Use the function from part A to determine how much of the substance will remain after 4 years. Okay, that's as simple as plugging it in. So we have 250 e to the, I can get by second ln, negative 0.4621, and t is going to be 4 times 4, and we get 39.3722 grams, which, if we check, should be pretty close to our original answer. Maybe a little off because of the rounding. This was the same problem as the first one we did. 39.3824, 39.3722. Pretty close. And in fact, I'll show that they're actually equal. We'll do an exact value because I know I did one of those before. Okay. Problem 6. Same game. I'll run through this very quickly. 600 grams are initially present, so 0,600 is a point. 3 years later, only 300 grams are. So the half-life is obviously 3 years. Function a e to the kt. Okay. 600 equals a e to the k times 0. That makes 600 equals a. And then 300 would equal a e to the k times 3. A is 600. 600 e to the k times 3. Divide both sides by 600. ln both sides. And the ln e winds up canceling. So here, k will be approximately equal to ln a half divided by 3. ln 0.5 divided by 3. K is approximately negative 0.2310. And you notice the k is negative. And that tells us something. That tells us that this is going to be exponential decay. I can tell. The same way where here, when b was between 0 and 1, and in this case, b is always between 0 and 1. That means the more I multiply by, the smaller my value gets. Remember end behavior of your graphs. Here, I don't have to look at the b, I can look at the k. If k is negative, I'm decaying. If k is positive, I'm growing. So here, f of 4 is just plugging in 4 into my function. Whoop, I didn't find my function yet. A e to the k t. So an f of 4 would just be plugging 4 into here. And this is something that you can try and just check to see that this is similar to the answer we got to problem number 3. Sorry, problem number 2. Should get a very similar number. Okay. And in fact, just as a quick little note here, if I do e to the negative 0.2310, I get 0.7937. 0.7937. The e to the k is the same thing as the b. The little a in my ab to the x and the big A in my ae to the kt are both the same. And here, the second constant is being raised to the x. Well, e to the kt is the same thing as e to the k to the t. So my b is the same thing as e to the k. So just a little note, and we'll talk about that in just a second. A radioactive substance is decaying such that after 2 years, there are 300 grams of substance remaining, 2, 300. After 5 years, there are 100 grams, 5, 100. So we need f of t equals ae to the kt. So we'd have 300 equals ae to the k times 2. And then we have 100 equals ae to the k times 5. And you note again, we don't have an initial value, so I'm going to have to divide. Same game as before. 3 equals. The a's cancel. The e's are the same bases. So this is 2k. This is 5k. This will be e to the negative 3k. ln both sides. The negative 3k comes in front, and ln of e is just 1. So then we get that ln of 3 is equal to negative 3k. So we get that k is equal to ln 3 over negative 3. And now here's what I'm going to do. I'm going to leave that like that for now, because in the last problem in the first part, we left these as exact values. And then I'm going to use this to plug in here. So then I'll plug into the first one like I did before. 300 equals AE to the ln3 over negative 3 times 2. So then this is 300 equals A e to the 2 ln 3 over negative 3. So then 300 over e to the 2 ln 3 over negative 3 equals A. So what is that approximately? And we should know what that is if we're talking about exact values. 1, 2. It should be 624.0251 when we round it, because right now I haven't done any rounding. So let's see. In the handy dandy calculator, we have 300 over e to the, and now this is a fraction, 2 ln 3 divided by negative 3. And we get 624.0251. And in fact, what was the k? It was ln 3 over negative 3. Well, what's e to that number? E to the, oops, not what I want, ln 3 over negative 3 is 0.6934. Well, nope. 0.6934, 624.0251. It's the same exact function. It's just expressed a little differently. Similar to the way we have point slope form for a line and we have slope intercept for a line. We have standard form for a quadratic and we have vertex form for a quadratic. We have standard form for a polynomial and we have factored form for a polynomial. So this function is going to be 624.0251 e to the, and now I can just round this. Delete. That is negative 0.3662. And then if I want to know after 4 years, I would just plug in a 4. So in part A of questions 5, 6, and 7, we model the situation using that. What does the A represent? Same thing. Initial value, or initial amount of substance, or it's the initial amount of whatever's there. What does the K represent? I'm going to tell you, you're not going to understand it, but I want you to remember this for next year. Right now, put it in your head, put it in the back of your mind, and just remember this for next year. The K is what is called a constant of proportionality. Okay? And again, when we're talking about exponential growth and decay, we can either use f of x equals ab to the x, or we can use f of t equals ae to the kt. And the thing you have to remember is that this function, ae to the kt, is a completely different type of exponential growth than p times e to the rt. In this function, the a is an initial amount, and the k, while it has something to do with the rate, is not the actual rate. It is not the actual rate. It means something different. In this formula, the p is the initial amount of money, and the r is the interest rate. They look exactly the same. They look interchangeable. They mean different things. So please understand that. And that being said, this is applications of exponential growth and decay. Your homework is going to be in the textbook that I will post. So I hope you enjoyed this. And once again, this lesson gets the Cetron seal of approval. And we'll go with a little seal. We'll say that he's going to start off small, and then with some exponential growth, maybe he'll get bigger. Cetron seal of approval.